today we are going to see another aspect of the radial basis function, that is, we would look upon the radial basis function as an ill-posed surface reconstruction problem. Okay. We will say why is it ill-posed, but I think the aspect of surface reconstruction we have already given some introduction to it, because the whole problem, okay, we are having a new look at the training of a multilayer perceptron, in the sense that we are looking at it exclusively from the point of view of a surface fitting. Okay, that is to say that when the input patterns are given and the outputs corresponding to that are specified, then essentially the mapping that is done within the network, okay, that one we are using for the that one we are using as a function which we obtained by training, and then we are interpolating upon it, because the interpolation only would lead to the generalization. Now, in the last class we were talking about the interpolation problem as such, and we were making some mathematical formulation of it. Of course, things were done in a bit of hurry. So, I thought that maybe it is good to spend a bit of time about what we were doing in the last class. Okay. So, you remember that in fact what we had done in the last class is like this, that while talking about the interpolation problem, we said that we have been given this information, right, that we will have to reconstruct a function f(x). Okay. In fact, here one correction that we have to make is that we were saying that we have to find a function that maps from Rn space to R1 space, and this is wrong. Okay, so I told something wrong. This n is incorrect, because essentially what you are looking for is a mapping from Rm0 space to R1, because M0 is taken as the number of inputs, okay, or the dimensionality of the input vector, whichever way you refer to. So, it is Rm0 space at the input, and then we were considering the case of a single neuron. So, the mapping that we are looking for is essentially, it is this mapping function f only that we are going to find out, okay, which is essentially from Rm0 to R1. So, you please make corrections in your notes that it should not be Rn. Okay. In fact, immediately after the class, one of the students who were present here happened to point out this. So, I just make it a point to make this correction, that it is Rm0 to R1 space mapping. Now, what we are given with is all these points that we are feeding the training patterns, okay, and training patterns means that essentially we have got a set of all these xi's as the inputs, and corresponding to this fxi's means fx being the function to be realized, the mapping function to be realized, we will be having fxi is equal to di for I is equal to 1 to up to n, assuming that we are feeding n as the total number of patterns. Okay. Now, this means to say that all this fxi is equal to di is going to be fed as the constraints, okay, and as we had written down that we have to, if we have to model it in terms of the radial basis function networks, then we are going to write it as fx is equal to summation of wi phi, and the phi's argument is the norm of x minus xi. Okay. And here we are adding it up for I is equal to 1 to n. So, this is acting as a linear summation, weighted summation, just like the way we were doing in any neural network. Okay. So, that means to say that after the input space x is mapped into the corresponding phi space, okay, then what we are doing is that from after the x to phi space mapping, we are just linearly combining all the phi space outputs, okay, and then having that as our final output. Okay, that is exactly what we are doing. Now, if we look at this equation, then you can see that it means to say that since we have got x minus xi over here, and what is this xi in this expression? In this expression, xi acts as a center of the basis function. Okay. You see, I mean, we were taking the examples of the Gaussian basis function in the last class. Okay. So, if we are taking the Gaussian basis function, then giving an xi like this would mean that you are shifting the origin of the Gaussian function. Okay. That is you are making a shift by adding the x1 I mean xi to it. So, this xi is acting as that. So, that means to say that because we have n such patterns, okay, we have got n such different xi's, which means to say that, as if to say that we have got n different radial basis functions. Okay, we have got n different radial basis functions which we are obtaining as x minus x1, x minus x2, x minus x3 up to x minus xn. So, n patterns, that is what we are having, and we are assuming that we have got n such radial basis functions. Not that we always require that. In fact, you remember that the last example which we were taking was that of an exclusive OR, and in that exclusive OR example we were taking 4 patterns. I mean, we altogether have 4 patterns, right? The set of 0 0, 0 1, 1 0 and 1 1. Okay. But we were considering in the last example, okay, only 2 of those radial basis functions where we made the radial basis function, I think, centered around 0 0, and another we took which is centered around 1 1. Okay. We did not take the radial basis functions centered around 0 1 or 1 0. Okay. We avoided taking it. In fact, we could have taken that also. Okay. If we had taken, I mean, we did not take it because we could solve the problem. We could make it linearly separable in the phi space, but there would not have been any harm if we had taken 4 such radial basis functions also, because there are 4 patterns. Okay. 4 would not have made it any harm. In fact, if we had transformed that into a 4-dimensional space instead of a 2-dimensional space. So, from the 2-dimensional input space to 4-dimensional phi space if we had mapped, okay, and that too non-linearly because the basis function itself is non-linear, then our separability would have been even better than that, okay, because then, I mean, we would have got both the advantages of non-linear mapping as well as the higher dimensionality space mapping. So, here indeed we are, I mean, writing this equation or writing this expression with the thinking that normally our n, that is the number of patterns that we are feeding, should be sufficiently greater than that of m0. So, which means to say that if we are having n such basis functions, n such phi functions, okay, each of these are centered around all these xi's, okay, then naturally we are mapping from the m0 space to an n-dimensional space, which is a mapping into a higher dimensional space. So, in other words, okay, I mean, let us consider that there are n such basis functions and we have obtained the fx like this. Okay. Now, this we can in fact, I mean, after putting the interpolation conditions, because this fxi is equal to di, this is a constraint or the restriction that we have to impose upon this equation, because at all these points we know, I mean, when x is equal to any of these xi's, any of these given xi's, we know that what its output is going to be, its output is going to be di. So, simply what we will be doing is that we pick up the first, so let us say that out of this xi we pick up the x1 first. So, we will put fx1 in this equation, fx1 is nothing but d1. Okay. So, we will be having an equation like d1 which will be realized as the summation of wi phi x minus x1. Okay. We will be using, no, we will be using x minus xi only, x minus xi. I mean, all these n basis functions, n radial basis functions will be used in order to determine this. So, we will be having all these weighted summations added up, all this weighted summation of n different radial basis functions will be added up to form fx1, and like that we will be having fx2, fx3 like that, or rather in so many words computing the d1, d2, etc. So, if we do that, then the resulting matrix equation, I think we had written down in the last class, but no harm in repeating that, just for our ease of reference. We can write down here that we are, as if to say, that having it as phi 1 1 up to phi 1 n, phi 2 1 up to phi 2 n, phi 2 to phi 2 n, okay, and then lastly phi n 1, phi n 2 to phi n n. Okay. Does not mean that we have got now n square number of basis functions. So, let us not make that mistake. We are not having n square number of basis functions, we are having n number of basis functions only. But the notations, but now we are using the double subscript. So, the meaning of this double subscript should be clear to you, which I am going to write. Let me complete this. So, this W1, W2 up to Wn is easily understood by you. So, they are the n number of free parameters, because all these n outputs of the radial basis function space, okay, they have to be linearly added. So, this becomes equal to d1, d2 up to dn. Okay. Now, here the meaning of this double superscript, double subscript is that in this we define phi j I as the phi function of xj minus xi, okay, norm of this, and where j I, okay, both of them vary from 1 to n. So, you can see that our basis functions still remain as n such basis functions only, but you see that when we pick up x1, then what we do? Okay. Supposing this xi we have fixed to something. Let us say that xi I have fixed to, we are taking the very first basis function. So, xi in this case is equal to x1, okay, and supposing we take the first of these, okay. So, then yes, supposing we take this fx1, the first one. So, fx1 means that we will have to add the responses of this from all these. So, that means to say that we have to add up that x1 minus x1, x1 minus x2, x1 minus x3, like that all these n outputs will be added. But because we are having x1 minus xi, okay, and similarly we will be having while computing fx2 we will be having x2, we will be having x2 minus x1, x2 minus x2, x2 minus x3, like that. So, in a sense, okay, we are making the computation of this n number of times. So, in effect we are forming an n by n dimensional matrix. So, please do not misinterpret, that is, it is as if to say that I am realizing n square number of basis functions. The basis functions still remain as n. Now, what I do is that we define, we just want to represent this equation in a compact mathematical form. So, what we do is that we define D as the vector d1, d2 up to dn, okay, the transpose of this, and the w vector will be defined as w1, w2 up to wn, okay, again the transpose of this, and phi we have already defined, okay. Phi will be what? Phi will be the set of phi ji's, okay, given that ji is this 1 to n. I am not writing the whole thing again. So, this is the definition of phi. So, this is d, this is w. So, simply this equation which I have written in the matrix form is now to be rewritten as phi, where phi is a matrix. In fact, phi should be a matrix. So, I am putting this notation. So, where phi multiplied by w, okay, basically rewriting this whole equation, is equal to what? This equal to the d vector, yes. So, phi times w vector is equal to d vector, okay. Now, what we are going to solve for the network? We are going to solve for the what? W. We are going to solve for w. So, how are we going to solve it? We can solve for w as this, that w should be equal to phi. Again, you see that here phi is becoming a square matrix, okay, n by n matrix, and assuming that the inverse of this exists, okay, that means to say that assuming that the phi matrix is non-singular, we can write that phi is equal to, W is equal to phi inverse times D. All right. So, what do we need? Very simple. We have to determine these W's, okay. And in order to compute these W's, what we need is these D's, which will be given to us, all the training patterns will be given to us, and then we have to compute this phi inverse. Phi inverse means, okay, basically we have to have the knowledge of phi's, and knowledge of phi's is not difficult to obtain because we have got n different basis functions already defined for us, n different basis function with each centered around the given patterns, okay. And then we compute the matrix of that, the phi matrix, and then we are taking the inverse of this. So, this is possible, okay, assuming that phi is non-singular, and therefore, phi inverse exists. Now, this is a very important question, okay, that how do we assure that phi is non-singular. In fact, in recent years, okay, good amount of work has been done related to the radial basis functions, okay, and there are some typical functions which have been found out to be non-singular. I mean, if we are taking those functions as our basis, okay, then the phi matrix that we will be getting, okay, then those phi matrices that we obtain is going to be non-singular. And let us have a list of some of those functions, okay, which are of interest to us, that means to say the functions which can be used as a radial basis function. And some of these very popular functions are, okay, so we can write down functions of interests in RBF, and those functions are multi-quadrix. Now, multi-quadrix expression is given as phi r, okay, is equal to r square plus c square to the power half, where c is some constant, let us say for some c which is greater than 0, and r is a number that exists in the real space. We can say as R, just the R space, one dimensional real space, but of course, the same definition could be extended for the multidimensional case also. Okay. There what we have to replace is that there R will be replaced by the vector that we will be feeding as inputs. So, this is multi-quadrix. Okay. Then another function which is used as a radial basis function is the inverse multi-quadrix. And the inverse multi-quadrix is given as phi r is equal to 1 by r square plus c square to the power half, okay, for some c greater than 0, and r is less than or equal and r belongs to this R space, the real space. And then the third is of course the very popular Gaussian basis function. So, for Gaussian basis function, okay, in the R space if we write, then it is phi r is equal to exponential to the power minus r by 2 sigma square, okay, minus r square, sorry, yes, that is what I realized, that some mistake. So, for some sigma greater than 0 and r belonging to R. So, these three functions, okay, they are used in the RBF, and the reason why we can use them in RBF is because if you are composing the phi matrices out of this, okay, out of any of these functions, okay, then phi inverse is also existing, is seen to exist, and because of that, okay, these can be used for the radial basis function applications. The only restriction, and I think it is quite logical also, is that the set of xi's that you are choosing, okay, the set of xi's that you are choosing, they must all be distinct. So, I can say that if we take xi, okay, for I is equal to 1 to n, okay, we are saying that all these things must be distinct to ensure non-singularity of the phi matrix and phi matrix is given a name. What name would you think should be more suitable to the phi matrix? Let us name that phi matrix. It is used for what? Phi matrix, any good name for phi matrix that we can give? Radial basis function matrix, okay. After all, we are using it for interpolation, so we can term it as an interpolation matrix. So, we can say that this must be distinct to ensure non-singularity of the interpolation matrix phi. Okay. Now, we can have a quick look at these functions, okay, that we have already defined: multi-quadrics, inverse multi-quadrics and Gaussian. Some of the properties which becomes very obvious out of these three functions is that, look at the multi-quadrics. If you increase r, okay, as r tending to infinity, okay, what is happening? Phi r also tends to infinity. So, that means to say that this is not a local function, it is increasing. So, we can say that this is a non-local function, okay, in the sense that it becomes unbounded as we keep on increasing this r, all right. Whereas, inverse multi-quadrics and Gaussian, they share a common property. As you make r tending towards infinity, okay, you can see that the phi r function tends to be 0. Okay. In fact, here this c square is there, okay, but as r tends to 0, okay, it is 1 by c. We have very small quantity, normally c is not chosen to be very high. So, you can then have the phi r as tending to 0, okay. So, this is more a localized function, okay, and even Gaussian also is localized function, okay. Now, it is seen that for these localized functions, okay, which are realized out of the inverse multi-quadrics and Gaussian, okay, the phi matrices which are realized out of them, out of these two functions, they happen to be positive definite. And so, obviously, their phi inverse exists, okay. Now, this one multi-quadrics, although it is not positive definite, okay, because of this property that as r tends to infinity, we find that it is the function is also tending to infinity. So, it is not positive definite, but even though it is not positive definite, still the phi inverse exists, and one can use these radial basis functions, okay, for the interpolation problem over here. So, this is all that I wanted to talk about interpolation, but let us now see that whether such kind of interpolation is always going to be good for us. You see, now what we are we are trying to say is that, okay, you have to train a network with m0 number of inputs. You have to generate a single output. I mean, that is the example with which, I mean, that is the condition with which we proceeded. You can generate multi-dimensional outputs also, there is no harm, it is just a simple extension of that idea. But you have to do this kind of thing by feeding n different number of patterns, okay, where you are assuming that n will be sufficiently large as compared to m0, and you will be using for n corresponding to n different patterns, you will be using n different radial basis functions. Now, mind you, one very important thing to note here is that we have taken n patterns and we have taken n radial basis function. So, the realized matrix that we had got is an n by n dimensional matrix that we got, and the non-singularity conditions etc., are coming for that n by n matrix. If we had chosen less than n, then such kind of a non-singularity is not always guaranteed. Okay. I mean, we may be luckily finding out the reconstruction problem. I mean, we may be having, I mean, somehow generate a linear separability in the phi space and feel happy about it, but I mean, all the time it is not possible. The thing is that in that case, what is to be ensured? That if there are n patterns, you need n radial basis functions, right? And I think the natural thinking is that in order to have a good surface fitting, you should have as large a value as for n as possible. More number of training points, okay. I mean, if you are having, I mean, in order to learn better, what we do in real life, we read more and more examples, isn't it? Okay. But very often we also come across this situation that learning too many examples is also not good. Okay. Supposing I mean, somebody is trying to learn mathematics. Okay. Now, he just sees some book where there are some worked out examples, he studies that, and then he goes in for another book. Okay. The approach of that could be different, maybe one or two problems are solved wrongly. Now, if he sees too many examples, okay, then maybe that at times he will feel confused, and ultimately when the student is asked to solve an unknown problem, okay, that student would find it difficult to answer to that problem, because he has got lot of confusions in mind by taking too many examples. Why? Because I mean, he has picked up 5 or 6 books in mathematics, and maybe that 1 or 2 books are not really good books. Okay. Their approach might be different, their examples are not good. So, such 1 or 2 books are, I mean, we can say noisy books. Okay. So, likewise, if you are having too many number of patterns, okay, taken from the real life, there will be some patterns which are noisy. But in this interpolation problem which we have discussed so far, what are we trying to tell? We are trying to tell that, okay, interpolation means that inevitably all the points that are known to you, the surface must pass through that. Okay. Now, there lies a problem. I mean, if we constrain always that through every training pattern, the fitted surface must be passing, okay, and we will be having the interpolation in between, then it not only learns the good patterns, okay, it also tries to learn the idiosyncrasies that are present in the pattern set. All the noise that is present in the pattern set will also be there. So, strictly looking at it from an interpolation point of view is not the best thing that we are looking for. Okay. We should also try to make it noise free, and how do we make anything noise free? Okay. We try to smoothen, okay, whatever surface we fit. Okay. If after fitting that surface we try to smoothen it out, okay. Why are we smoothening? Because we are not totally relying on the data set that we have got. We assume that inherently there is some amount of unreliability in the data that we had got. So, that is why after, I mean, fitting the surface, okay, we try to smoothen it out. Okay. That means to say that during the surface fitting itself, okay, we should try to evaluate that whether we have not only minimized the errors. See, minimization of error is one of the considerations. Now, definitely if you are fitting a surface, okay, through a set of given points, naturally you have to have a situation that the error between the fitted surface and the corresponding actual points, okay, if you take those errors, square it up and add it up, okay, make it as the sum squared errors, okay, those sum squared errors, okay, you can minimize. That is what we have been doing for so long, okay. But we are saying that if you have to, I mean, look at it from the point of view of avoiding such kind of results, or our surface interpolation problem getting affected by the idiosyncrasies of the data or the noise present in the data, then we should do something more. Then we should, in addition to this minimization of the error, we should also try to see that there is some aspect of smoothing that is to be done. Now, mind you, because we have such kind of noisiness which are present in the data set itself, okay, the problem that we are going to solve, this surface interpolation problem that we are going to solve, is not a well posed one, it becomes what is called as ill posed one. Now, some people may not be very familiar with these two terminologies of what is meant by well posed and what is meant by ill posed. So, I would like to spend a bit of time, okay, in order to make it clear in your mind that what is a well posed problem and what is an ill posed problem. And in fact, we are going to see that this surface interpolation is an ill posed problem, okay. It cannot be reliably solved, and in order to solve it reliably, we have to make an ill posed problem into a well posed one by making some kind of transformation, which we will be discussing shortly. So, essentially this we are now looking at the hypersurface reconstruction problem as an ill posed problem, but again digressing a bit, that what is meant by ill posed. And in order to know what is ill posed, the definition that I would like to simply say is that whatever is not well posed is ill posed. Okay. If somebody is not well, he is stated to be ill. So, if some problem is not well posed, that is an ill posed. So, we must know that what is meant by well posed. So, well posed problem definition we can just put forward over here. So, well posed means that let us take a, in order to define it, let us take a domain X, okay, and correspondingly we take a range Y, okay, in the metric spaces, and they are related, this domain and the range are related to each other by a mapping function, okay, related to so the domain range is related to domain, okay, related to they are related by a mapping function, by we should say by a fixed but unknown mapping function. We do not know that what exactly that mapping function is, okay, we are going to determine. Okay. Now, having defined this, that it is just a mapping from the domain to the range, okay, using a mapping function. Now, when are we going to say that this mapping is a well posed problem? The mapping is said to be well posed, okay, if it fulfills three conditions. So, mapping is well posed if three conditions are fulfilled. And what are those conditions? Number one is existence. By existence we mean that for every x, for every x vector, okay, which are belonging to a set H. That means to say that from the domain we pick up, okay, all these x's, okay, and for every x belonging to H, okay, if there exists an output y. And how is y? Because we are considering the mapping function to be f. So, we are going to write y as f of x vector. Sure. So, yes, x, H is the space, okay. Yes, H is the set from which we are choosing this x domain, okay, set taken from the domain space, that is right. And y is the output of that. So, output will be expressed as f of x. So, there is an existence of direct mapping, I mean simple, okay, that you pick up any point, I mean supposing, I mean we can depict it using a small illustrative diagram. Let us say that this is our input set, okay, the range set, the domain set, let us say the input set, and supposing this is the output set, okay. So, we pick up any x. So, what the existence condition is saying is that you pick up any x which is defined within this set, and for every x there is a corresponding value in the y space, that is to say in the range space. So, if for every x present in this set, okay, this is the H set, okay, we obtain an output, then we can say that the existence condition is fulfilled. If for any one of the points, like say for example, if for any of these points we cannot compute, I mean given the mapping function we cannot compute any corresponding value of y. If the corresponding value of y becomes undefined, in that case we can say that the existence condition will be violated, because then the mapping from this space to this space for this particular point does not exist. So, the existence must be fulfilled by all the points in this set, that is what this definition says, okay. H being this set, that is the domain set. And the second condition is written as the uniqueness condition, okay. That is to say that there is a unique mapping, okay. And what is that I mean translated in analytical terms, that for any pair of input vectors, okay, let us take any pair of input vectors, we take one of the input vectors as let us say x vector, okay, and another input vector we are taking as say t vector, okay, and all these this input vector x as well as the vector t, okay, they are belonging to the set H, okay. So, if for any pair of these input vectors we have f x is equal to f t. Now, f x is equal to f t means what? F x is equal to f t means that as if that x will be mapped to this point and t will be mapped to the same point. So, two of the inputs, okay, we take and they are getting mapped into the same point. If that happens, then it is not a unique mapping, okay. So, for uniqueness condition to be fulfilled, you take any pairing x and t, any pairing you form out of all the patterns that are present in the H set, okay. If for all the mapping is distinctly different, okay, then it is unique. So, if so we have f x is equal to f t, under what condition f x is equal to f t will be there, taking any pair? Only when x is equal to t. So, we have f x is equal to f t if and only if x is equal to t, okay. So, that is the uniqueness condition, and then comes the third condition, which is called as the continuity condition. Okay. And what is continuity condition? Meaning that if for any epsilon greater than 0, okay, let us take it like this. Let us say that we have got here a point, let us say which is fx vector. We can write it as fx because it is already a mapped point, mapped from this x space to this. So, fx a point we are taking, and let us consider a region surrounding this point, okay, this point in the multidimensional space, of course. So, this is having a, this region is say having a radius equal to epsilon. Okay. Now, if for any such epsilon greater than 0 there exists a mapping function delta is equal to delta of epsilon, okay, such that I am going to explain it after I write down, okay, such that the condition rho x comma t, okay, is less than delta implies rho y, okay, fx comma ft less than epsilon. So, this means to say what? That we are taking again a pair x and t from the h domain, okay, and we are mapping it into the fx domain, okay, and in fx domain we are having that as fx and ft, okay, and there we are saying that here the bounding is that it is less than epsilon in this space, and if correspondingly we have here a bounding of, I mean taking x and t to be like this. So, if this is x and if we take region surrounding delta over here, okay. So, delta is the region that we are taking from the input space, then correspondingly it gets mapped into the region centered around this and with epsilon. So, delta is being mapped into epsilon, okay. So, if from this to this such a kind of mapping exists, okay, then it is continuity. Taking in a very physical, I mean if the mathematical definition seems to be little confusing, in fact it is not, okay, but one can also physically imagine also that that means to say that you take a small region, okay, and if that region entirely can be mapped into the, I mean into a bounded region, I mean you take the things within a bounded region in the input space, in the H space, and if it gets mapped into another bounded region in the output space, then the mapping is continuous. If that is not, then I mean there is a problem, then it is lacking continuity. So, if all these three conditions, that is to say existence, uniqueness and continuity, if all these three conditions are fulfilled, then only we are going to say that the problem is well posed. If any of these three conditions is violated, any, then the problem is not well posed and it is referred to as ill posed problem. And let us see that the problem which is at our hand now, that is to say the surface reconstruction problem, okay, using the radial basis function, if that is a well posed one or an ill posed one. Now, the thing is that, okay, first of all that let us see that when we are deriving the training set, okay, from the examples, okay, that is a well posed because we are taking, I mean the examples from the physical process itself, okay, and that is a well posed problem. But when we are doing a surface fitting, okay, then is it a well posed one or not, because the data may be containing lot of noise, the data may be contaminated with lot of noise which are present in the example itself. Okay. But noise is present in the physical process itself, and that is why we got the noise in the examples. So, physical process to example, that mapping is well posed, even though noise is present in the physical process, noise is also present in this. But the thing is that because of such kind of noisy patterns, okay, in fact, it can be seen that in typical cases any of these three conditions could be violated. You may be having some input points for which the output becomes undefined. If that is the case, okay, then you are violating the existence condition. Okay. Uniqueness definitely means that you cannot have a function to be multi-valued, but I mean, because here you can see that you cannot have, I mean, f x is equal to f t unless x is equal to t. Okay. So, uniqueness condition also can be violated in the sense that it may so happen that because of the noise x gets mapped to a point, t also gets mapped to the same point, although x and t are different, but x and t may be getting mapped into the same point in the output space. Okay. And noise can also drive you out of the continuity. Okay. So, because of this, all these three conditions, okay, can at times be violated, and that is the reason why the surface interpolation problem is always taken as an ill posed problem.
So, this continuity we can interchange with del and sigma doesn't matter much. In the continuity we can interchange the del and sigma, sir. It's the same thing.
That's the same thing. Yes, absolutely, absolutely. I mean, whether you take delta here and epsilon here, I mean, it is to say that one bounded, I mean, let us look at it this way, that it is a mapping from one bounded space to another bounded space, that is all. I mean, the mapping does not get unbounded. Okay. Now, the thing is that yes, because it is ill posed, but we want to solve it. Okay. And how are we going to solve it? So, in order to solve it, we should not look at it simply from an interpolation point of view, making a strict restriction that okay, it has to pass through all the points that we have defined in the training set. Let the surface be little more flexible. Okay. I mean, you have defined, let us say, I mean, you have specified a bed of nails and you want to put some surface over it. Okay. Does not matter that this surface has to lie on the bed of nails. I mean, you can play with your surface, you can make it smooth, okay, so that, I mean, the interpolation capability or the generalization capability of that is better and it does not get affected by noise. So, that means to say that we have to incorporate some kind of a smoothness condition also into it, and that is why and that is what is called as the regularization. So, I can say that it is the process of regularization, or regularization may appear to be little more sophisticated English. A more common English could be smoothness. Okay, we want to make the surface smooth, that is all. So, regularization or smoothness is used to make an ill posed problem into a well posed one. And in this case, we are going to make use of the Tikhonov's regularization procedure. Okay. So, we are going to make our mathematical formulation based on that. So, I mean, how are we going to do it? So, let us first take the input signal. Okay. So, the input signal for us is the set of xi's, okay, where xi's will be belonging to what? Rm0 space, okay. The input space is M0. So, it is 1, I mean I is equal to 1, 2 to n, okay, and the desired response that we have is the set of di's, okay. So, di, and in this case, in this example, we are having di getting mapped into just one, I mean we are assuming only one output to be there. So, di getting mapped into R1 space, okay. Again I is equal to 1 to n, assuming that there are n patterns, okay, and we considered the approximating function or the interpolation function, whatever you say. This approximating function is considered to be f of x, all right. Now, Tikhonov's regularization procedure that involves two terms, okay. And what are those two terms? Okay, two terms of Tikhonov's regularization are, number one is the standard error term, okay. And how are we going to define the standard error? I mean in our usual way, what we had already done earlier. So, that is the error term Es of f, we can write down as what? Half of summation di minus yi whole square, okay, summed up from I is equal to 1 to n. Di is the actual response and yi is the yi is the actual response and di is the desired response. So, that means to say that we are allowing the surface to deviate from the desired points. So, only if I mean if it is so that all the yi's are equal to di's, then the standard error term would have been 0, okay. But we may not want that, okay. We may not want it to pass through all the given points, we may allow it to deviate. So, that is why di and yi's are taken to be different, assuming that the surface may not pass through the given set of points. So, di minus yi whole square, adding it up over I is equal to 1 to n would give us a standard error of fitment, okay. In fact, instead of yi one can always express it as fxi, yes, that is correct. So, it is d minus fxi, because fx we are taking as the approximating function. So, this is di minus fxi whole square, this is the standard error term, okay. And then in addition to this, I mean where we are actually making it regularized or smoothened, okay, is done by the second term, which is called as the regularizing term. And the regularizing term is EC of f is equal to, can you tell me that how would you regularize a function? What? Yes? Can I just have the answer from one of you? Differentiate, yes. And what that differential should lead to? The differentiation result should be minimum, isn't it? Because if the differential, I mean if the derivative is small in magnitude, that means to say that the fitted surface is smooth, isn't it? And this differentiation we have to do in how many dimension? We have to do it in M0 dimension, okay. So, definitely we would like to do a multi-dimensional differentiation, and just like the way the error term should be less, okay, even the differentiation or rather the multi-dimensional derivative also should be less. So, the problem is now to be reformulated in the sense that instead of like we were doing earlier we were only saying that okay, minimize the error, that is all. Now, we are saying that not only minimize the error, but also have a smoothening on the surface. So, in order to import the smoothing into consideration, what we are doing is that we are introducing this regularization term, which is defined as half. Again, this half is to be used for a consistency, because the measure of this regularization is the derivative operator d, okay, on the function f, and d is very rightly written in the vector notation, because this differentiation or the process of taking derivative would have to be done in the M0 dimensional space, okay, and take the squared norm of this. Okay. This becomes your regularization term. So, here I mean we can explicitly write down that where d is a linear differential operator. And given these two terms Es and Ec, okay, one can combinedly put forward a measure like this. One can make a combined measure Ef, which is equal to ESF plus, shall I put ECF? I put it, but mind you, one thing which is to be noted is that if I put ESF and ECF, that means to say that, as if to say that I am giving equal importance to the standard error minimization and to the regularization. Now, whether I should give equal importance to not is a debatable question. So, to make it general and to play safe, that one can play with it, okay, let us put a term of ECF multiplied by lambda over here, where lambda is a regularization parameter, we can say. So, we want to play with it, we want to play with this regularization parameter, and how to fix up this lambda, okay, that we will discuss in the coming class, because again I am exhausting my time limit. So, thank you very much.